With that, I'll start the recording and I'll hand over to Felix Schwenninger, who's going to introduce our first speaker.
Thank you, Ian. So my name is Felix Schwenninger, and I have the pleasure here and the duty and the honor to introduce our first speaker of that conference, which is Gitta Kutyniok from Munich. And I'd like to say a few words about her career and also her relation to Ivota, which is not completely new, this relation. So Gitta did her PhD at the University of Paderborn in Germany, and after that spent some time in the US at various positions at renowned institutions such as WashU and Stanford and Yale. And in 2008 got her position as a professor at the University of Osnabrück. And after actually a short term, she moved to TU Berlin as an Einstein professor, where she stayed for quite some time, before moving to Munich as a professor of a Bavarian AI chair on mathematical foundations of AI. Her research is probably known to most of you here, covers quite a broad range of topics related to the Ivota, that is in particular applied harmonic analysis and function analysis. And words to mention here is definitely compressed sensing, where she has established really results that are very important. More recently, there is a lot of things going on in, say, machine learning and related things in terms of operator theory, and that's also what Gitta will talk about, as far as I see in her talk. So, Gitta, thank you very much for being here. Thank you for giving us this lecture.
Yeah, thank you very much for the very nice introduction, and also thank you very much to the organizers for the invitation. It's really a great pleasure and an honor for me to give this talk here. Now, I think we all know how tremendously successful AI is these days, but on the other hand, we also know that there are still certain issues, for instance, concerning non-robustness or in general concerning reliability. And so this is the point where a mathematical foundation has to make an edge, and so my talk will take you on a tour through the area of reliability of AI from a mathematical perspective, show you certain research directions where mathematics can make an edge, and in particular also relate everything to the topics of this conference, so to operator theory and also harmonic analysis, in particular applied harmonic analysis, and show you how these areas can actually make a difference and where they become involved. And so in that sense, I would also like to encourage everyone and to whet your appetite to this, I think, very exciting new general research direction, mathematics of AI, because I think all areas of mathematics have to play a role there to really make it reliable and to really understand it from its steps. Okay, so I think we all know that we are standing at the beginning of the fourth industrial revolution through AI. So we see changes already, in various areas like self-driving cars, robotics, telecommunication, then even more sensitive areas like the whole legal system. So in certain countries already decisions are not completely decided by AI, but prepared by AI, and also the whole job sector. And then certainly there's no area in sciences which is not affected at this point by artificial intelligence. And I think everybody got, a real awareness of that when ChatGPT came up. So then I think in the open public, everybody became aware that AI makes a difference. And so I think we are at the beginning of a really radical change of our society in its full breadth. Now, on the other hand, there were also warning signs. People were a bit worried that, we don't really understand it from its depth. So there was this interesting incident 6 years ago, where a researcher, Ali Rahimi, gave a plenary speech at one of the big AI conferences. And he said at this conference, machine learning, so in particular AI, is still at the level of alchemy. So we are still missing this fundamental deep understanding. And in particular, he said, computers learn through trial and error, have become a form of alchemy, do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one AI architecture over another. So what is missing is this deep theoretical mathematical understanding, and so this also raised a big discussion. And truly, there are still a lot of issues with it. So there are problems with safety. There were various accidents involving robots, and after all, a self-driving car is nothing else than a robot. There are problems with security. One can hack into those systems, for instance, hospital systems, take over control, modifying things slightly so that the AI makes a radically wrong decision, but the human would not recognize the change in the data. Problems with privacy. These methods are extremely data hungry, and so privacy violations happen on a daily basis. And last but not least, problems with responsibility. And with this, I mean that many of these decisions are still black box decisions. We don't understand how they are reached, and also decisions can be biased. In that sense, I think it's fair to say that one current major problem worldwide is the lack of reliability of AI technology. And so, in that sense, I mean, when we look around, and you saw it through the media, I mean, there are various general attempts to make it more reliable. I mean, there's, for instance, the AI Act of the European Union, where, for instance, the right to explain is in, so every AI technology has to come with algorithms which help explain decisions. And also the G7 started last year in May, the Hiroshima AI process, to also encourage companies to ensure that AI is reliable. But I mean, from our perspective, I think from a mathematical perspective, what is really essential, and otherwise we can never get reliability, is to derive a profound mathematical understanding. And so this is what this talk is about. And as said, I want to show you certain research directions and sometimes give you a glimpse and sometimes a bit deeper view so that you get an overview of this area. And if you're interested, then you can just jump in. Now, as said, I mean, these are maybe two of the main focus: operator theory and applied harmonic analysis. Okay, so let's start very slowly and let's introduce the workhorse for artificial intelligence, which are deep neural networks. Now, this whole theory is nothing new. So it started in 1943 with McCulloch and Pitts, and they wanted to introduce an algorithmic approach to learning. And so what they did was quite smart, because we humans, at least we believe that we are intelligent. So what they did was they wanted to mimic the human brain. Now, if you think back of your biology classes, the human brain consists of neurons which are interconnected. And so what they did was they developed a mathematical model for a neuron and then connected that to a neural network. How does this work? Well, I mean, a neuron works as follows. You have signals coming in. They might be amplified, moving through these dendrites. They're collected in the soma, and then the neuron decides whether to fire or not. And so a mathematical model for that looks as follows. We have here inputs, x1, x2, x3, and so on. They travel through these dendrites. They might be amplified. This is modeled by these weights. And what arrives here is the sum of wi, xi. And now the neuron decides whether to fire or not, depending on a bias b. And so in its most simple form, it checks whether the sum is greater than b or less than b, and depending on that, it fires a 1 or a 0. And so this is the most simple form of an artificial neuron, and you can connect that to a neural network, and these are the free parameters, so the weights and the biases, that's what learned to the learning process. Yeah, so that looks very, very simple. And in fact, there are more sophisticated definitions for that. So let me first state a general definition for an artificial neuron. So you have these weights, W1 to Wn, a bias term, an activation function, rho, and an artificial neuron is then a function which is defined in this way. So you see from the previous slide, you have the sum, you have the bias term b, and now we have this activation function which is univariate, and on the previous slide, the Heaviside function was chosen, but this looks a bit simple. Now if you just output a 1 or 0, this will not, be sufficient from also an approximation viewpoint. You can choose a smooth function, for instance, the sigmoid, but what is used these days always, typically, is the so-called rectifiable linear unit, which is the max of 0 and x. Yeah, just a very simple spline function, but for some purposes, let's say, or for some reasons, this is what is usually enough for applications, and it's also very easy to program. Okay, so now, we have these artificial neurons. We connect them. Just let me give you an example. We have here these artificial neurons. You see here, they get their inputs, and they have their outputs here. So if you connect them in this way, how does it look like in mathematics? Well, here we have our input neurons. Then this is modeled. These connections are modeled by this weight matrix. You see here the first output is this weight times x1 plus this weight times x2, which is this line. This is this weight times x3, which is this line, and this connection is mimicked by this line. Yeah, so then here we add the bias terms, and we apply the activation function. So this is this part here. And then we keep going. So this is now modeled by this weight matrix. So we move from R3 to R2. Again, we add a bias term, and so on and so on. And so if you see this, it's a highly structured function. It's a composition of affine linear functions and nonlinear activation functions. And so you can imagine what the general formula will look like. So in general, a deep neural network looks like this. It's a purely mathematical object. You have here these affine linear terms, a weight matrix times x plus a bias term, and then you have here the nonlinear activation functions, univariate, and they are applied component-wise. And so the connection to a neural network we already discussed on the previous slide. So what is typically important is the number of layers. So these days, I mean, people can train neural networks with billions of layers. But the number of layers coincides exactly to the number of affine linear terms. And so why this is so powerful these days, there are two main reasons and why it didn't work in 1943. Because now we have this huge amount of data to train neural networks, and also we have the computational power to train deep neural networks. Now, what are the key mathematical directions? For this, I would like to take you once through how we apply neural networks, and then we will see what the key directions are, which we need to understand to make it reliable. Okay, so neural networks are there to approximate complicated functions, or also distributions. So let's say I have a function which is defined on a lower dimensional manifold, which is maybe a classification function, and computer scientists like to separate cats from dogs for some reason. And these natural images lie on some lower dimensional structure. So let's say all cats are mapped to the value 1 and dogs to the value 2. What we don't have is the complete function. We just have sample values, certain images, and we know whether they belong to one category or the other. So these are our sample values, and from these we now want to learn the function f. Okay, so what we do at the first step is we split this into a training and a test data set. We set the test data set aside and only use the training data set for now. And then the problem already starts. So which neural networks do we take? How many layers does it have? How many neurons each layer? Which activation function? Maybe we also don't want to have a network which has all connections, but we want to pre-select certain edges to be removed at this point. That means setting certain entries of these weight matrices to 0. And so then we train. Training is an optimization procedure. You see this here. Let me walk you through that, what happens. So this is the neural network function which we want to learn. And remember, what we need to learn are these weight matrices and the bias terms. What we want is that this neural network function applied to xi, these are the sample values, are close to f of xi, which we also know. And the closeness is given by a loss function that could be the square loss, for instance. And so then we sum over all training samples and we optimize. And so these problems are typically solved by gradient descent. Here we have the slight problem that we have millions of training samples, so gradient descent will not work because we cannot compute a million gradients each time. And so what people then use are what's called stochastic gradient descent, so that you randomly select certain of those samples and compute the gradients only for those. And so that hopefully gives you a good average. Now, if you've done that, you have learned your affine linear functions, you have now the neural network, you fix everything, and now you want to check how good it does on out-of-sample data. And so this, what happens there is, you apply it now to these xi's from your test data set, which the network has not seen before, and hopefully it approximates also f of xi there. So these are the steps. And from this, the key mathematical directions now arise. The first is what's called expressivity. And here I should say, computer scientists are extremely good to find catchy names. So I think we would say approximation. But expressivity, sounds quite nice. Okay, so that's expressivity. So this asks the question, how do you set up a network architecture? How many layers and so on? To get good performance. And so here, people use methods from applied harmonic analysis, approximation theory, and so on. The next step was the training process. So these are optimization questions. So here the question is, the problem is highly non-convex. Still this stochastic gradient descent, although it needs to optimize over a very erect landscape, typically finds a good local minima. And so the question is why, and this area aims to understand that, and certainly optimization, optimal control play a huge role, but also I might say a bit more exotic areas like algebraic differential geometry are now thrown into the game because people aim to understand the shape of these local minima. And here you see already, that basically, various areas of mathematics play a role. In particular, if there are new methods, then they typically have an edge and get additional insight. Then generalization, can we get overall success guarantees? So what we need are error bounds. And that we don't have these error bounds for the performance is the reason why some people in applications don't use them at this point. For instance, in electron tomography. In electron tomography, they don't have a ground truth. They look through everything through an algorithm, so they have to trust it completely. And so because of that, they need error bounds and success guarantees. So here goes learning theory, also operator theory, probability theory, statistics. If you think about it, and if you view this learning problem as a statistical learning problem, these are exactly the three components. There's the approximation component from the hypothesis class, there's the component from the algorithm itself, the error component, and there's the component from the out-of-sample error. Now, once you have trained everything, then you have another problem. If you cannot get access to your training process and you just bought this product, you have to understand how it works. And that's this area of explainability. And that relates to what I said before, that these regulations typically incorporate this right to explain. So here, you have a trained neural network, how does it reach a certain decision? So basically it's like you can view it also as an operator identification problem in a certain sense. You have the output, and you want to understand which, let's say, mechanisms led to that output, what were the key ingredients of the input. And last but not least, an area which is completely neglected, but I think also in particular from a mathematical viewpoint, we know has to be asked, and are there limitations. Right now everybody thinks AI is a Swiss Army knife, but there are limitations, and so the question is, what are the fundamental limitations which occur? And so if you're working, someone working in numerical analysis here in this room, we will discuss a little bit also in this direction just at the very end, but I think what I say there also concerns many other algorithms in numerical algebra and numerical linear algebra. Okay, so this is, as I said, mathematics for reliable AI. Let me just say, this is not the main focus of this talk, but let me just say that also there is, let's say, AI for mathematics. And so there are two main directions where these methods are now predominantly applied in mathematics in general. There are inverse problems where people ask, how can I optimally combine AI based with model-based approaches? So I have my traditional regularization approaches. How can I bring deep learning in? And there's the area of PDE where two main questions are asked from a numerical standpoint. AI and deep neural networks are extremely effective in the high-dimensional regime. So how can AI circumvent the curse of dimensionality, and vice versa, can AI also be used to learn physical laws automatically? Okay, but let's go back to this list. And you said, so these topics of this talk, popped up at some point. And so I would like to just now give you a very short glimpse into expressivity, just to touch this area so that you see a bit what this is about, because that is, this area is also important due to the fact that, this sets up the stage, which neural networks to take. Then the area of generalization is like the holy grail of neural network theory in a certain sense, and here I would like to delve a bit deeper in, because there are also certain directions from operator theory will pop up. We'll talk a little bit about explainability, and then just, if time permits, also about limitations in the end. Okay, so a glimpse into expressivity. This is the question, what is the approximation power of neural networks? And there's a very classical result, which I think should be in every talk about mathematics of deep neural networks. It's this approximation theorem, which you can see here, which says that if I have a continuous function defined on a compact domain, I have an activation function which is continuous but not a polynomial, then I find for every epsilon, for every accuracy, a neural network which looks like this, so a shallow neural network with one layer, which approximates this f with this accuracy. So in that sense, shallow neural networks can approximate continuous functions on compact domains with arbitrary accuracy. But then you don't know, I mean, what is the complexity of these neural networks and so on. But I mean, here, from our standpoint, now from an approximation, from a harmonic analysis viewpoint, you can say there are many methods in harmonic analysis which are used for approximation. Are they maybe better? And so I'm sure many of you know about wavelets, which are now a standard tool for approximation, for decomposition, and there are a lot of other applied harmonic analysis representation systems which are used for various tasks. Also, I mean, operator decomposition and so on. Yeah, and so, I mean, shearlets are maybe a bit dearer to my heart because we developed them. So here you see some of these shearlets. And so the question is, I mean, what is the difference between applied harmonic analysis methods, which we worked on for a long time and very sophisticated, versus these new tools from deep neural networks? And, well, unfortunately or interestingly enough, I mean, what we could show some time ago was that, I mean, these deep neural networks indeed achieve optimal approximation properties of all these affine systems combined. So they have this amazing universality property that they're better or at least as good as all those systems from approximation viewpoint. And so I think that shows, I mean, also the power of this approach. And in fact, I mean, one secret is also in this compositional structure. Yeah, so you have these different, if I go back, maybe let me go back to show you. Yeah, so you see here this compositional structure. Yeah? So this makes a huge difference, and this is not fully understood also from approximation viewpoint why. Yeah, and interestingly enough, I mean, you can even show that neural networks can learn these elements of representation systems from applied harmonic analysis. Yeah? So if you have a linear singularity, you can train neural networks with specific structures to then indeed learn something which looks like ridgelets, and you can do the same for these curvilinear singularities where something like shearlets can be learned. So in that sense, I mean, neural networks are extremely universal, extremely flexible, and in particular now in this area of applied harmonic analysis, expressivity can make a huge difference. Okay, so this was a short glimpse into expressivity, because that's not the main part here. Let's go to generalization. Now, generalization, as I said, is the holy grail. This is what people really aim for, error bounds on the test data set. So to understand how neural networks, which are then trained, behave on other types of data they have not seen before. And there's a surprising phenomena. So maybe first take a look at this. This is a statistical learning theory. Let me walk you through that. Here you see the size of the hypothesis class. So this is the size of the neural network, and this is the error. Now, when the neural network becomes larger and larger, it is more expressive, and certainly the training error will go down because it fits the data better and better. So this is not surprising. But the test error goes up at some point again. And this is this overfitting phenomenon. And this is very well explained, and this overfitting you see here in the top row. Yeah, so if you have two classes which you want to distinguish, and your neural network is not expressive enough, it can just draw straight lines, you do a really bad job. If it is a bit more flexible, I mean, you can do something like this, which looks already very good, because this green dot might be an outlier. But, I mean, if it's too flexible, it might do its job too good. Yeah? And so this relates to this overfitting phenomena. So then, I mean, another green spot might be misclassified. Yeah, and so this is what this explains. But now what truly happens these days is actually this, that after some point the test error goes down again. And this is modern interpolation regime. And so people still aim to understand that. And that's also the reason if people ask you which neural network to take, people typically say take the largest which fits in your GPU. So there, I mean, the larger, typically the better. But I mean, from also a mathematical standpoint, you want to understand, maybe we can still, get away with smaller networks. And so there are a lot of approaches. We see dimension, Rademacher complexity, neural tangent kernels, and so on and so on. But here I would like to show you one approach, which is more a functional analytic approach, and that takes us to the world of graph neural networks. And so there we can ask a special question concerning generalization, which we can then fully solve. Okay, graph neural networks are, neural networks which are a generalization because you can view Euclidean data also as a graph. Euclidean data you can view as a linear graph where each node has a value. So here graph neural networks now handle signals on graphs. So graph signal is just a map from the graph nodes to RC. And people are very excited about those because graphs appear everywhere these days. In recommender systems where obviously fake news detection, social networks are graphs, and then also chemistry, these are also graph structures. Now, for graphs, if you have a graph as an input, again, you have to ask this generalization question. So what you want is you have graph signals which are unseen in the training set, and you want to understand how good a neural network behaves on those. And so let's assume this graph on the right-hand side is in my training set, and then I input this graph on the left-hand side. But now you see here that these graphs look kind of alike. And so the question now I want to ask is, if two graphs model the same phenomena, whatever this means, you make this precise, then this graph neural network should have the same repercussion on both graphs. And so in that sense, this is a partial question of the true generalization question. I ask, if I have something in my training data set and then I have other graphs which are in the same vicinity, then can I get error bounds on that? And so we will prove that for spectral graph convolutional neural networks, and convolution operators will play a major role here. Okay, so these graph neural networks, as said, they are generalization of normal neural networks. Remember, normal neural networks, we have these weight matrices, and then we have the activation functions. So here we have now, instead of weight matrices, we take convolutions, convolutional operators, and you can view them, as we all know, in two different ways. You can do it spatially, you can do it spectrally. Now, spatially, you have, let's say, your filter with your slide over your domain, and spectrally, you do everything via the convolutional theory. And we will go this approach, and we will define that very precisely which convolution operators we take. And in fact, we will see that this makes the difference to achieve this result. So the activation function is similar. We just apply it component-wise. And there's another layer for these convolution structures, because this kind of blows up the dimension. You have always in between something like a coarsening, but let's not focus on that. Okay, so the key point is, how do we find this convolution operator? Let me just remind you. So we have our graph, and the graph is associated with the degree matrix and the adjacency matrix. We have then a graph Laplacian, which is the generalization of the normal Laplacian to the graph setting, which is this difference, and then you can also normalize it. So this gives me a self-adjoint operator, and it's a canonical generalization. The eigenvalues are frequencies, and the eigenvectors Fourier modes. And so this graph Laplacian somehow encapsulates the geometry of the graph. You can see this here if you have a graph, which is kind of, this is, let's say, the continuous version of a graph. But what you see here, you have different frequencies. You have your low frequencies, and then you have your higher frequencies according to the geometry of the graph. Okay, so how would you normally define a convolution operator in this sense? You would define it in this way. You have your graph Laplacian of your graph. You have eigenvectors, and then the spectral graph convolution operator you would typically define this way. You have here some filter coefficients, and as said, these are the eigenvectors. And so this would be your convolution operator, which you then would apply in each level, and what you would train and learn are these coefficients. If you would do it that way, you have a lot of problems. So first of all, it's computationally demanding. You have to compute the eigendecomposition, and if you have these friendship graphs, that's just not possible. Also, typically this is computed by an FFT, but there's no general FFT for graphs. But worse, it's not transferable. So imagine you have a graph and you perturb it slightly. Then sure, I mean, the graph neural network should behave somehow in a similar manner. But if you perturb it slightly, these eigenvectors can change a lot. So that means this operator will change a lot because these CJs are fixed. Yeah? So this is a huge problem, and so we have to be smarter than that. And so here, I mean, these areas like functional analysis, operator theory plays a major role to design graph neural networks which are then transferable and which even in certain instances then behave better than normal the spatial networks. Yeah, and so the key here is functional calculus, to use functional calculus in that sense. Yeah, so functional calculus, I mean, everybody of you is aware of that. So we have self-round operators, and then we have a function g, continuous function or bounded function. And we have this decomposition, and we have a very nice situation if g is rational, because then we can write g of t down exactly. And the key point now is to replace these CJs, these discrete objects, by something continuous. Yeah, so instead of learning these CJs, we will learn a function, and that will make a huge difference. So instead of using that convolution, we define convolution in this way. And so what you see here is that we replace basically the CJs by this G. So instead of learning the CJ, something discrete, we go to the continuum function analytic world. And we learn this function G. And so we then define this convolution operator by G applied to the graph Laplacian, and that gives me this decomposition. And that makes the key difference, because first of all, we solve the instability problem. If my graph changes slightly, then these UJs will change a lot, and also here. But the lambda j's as well, and that counterbalance it. So then this becomes stable. It also solves the computational problem, because here, I mean, we need to compute the eigendecomposition, but here, if the g is a rational function, we can write g of the graph Laplacian exactly down. We don't need an eigendecomposition anymore. Yeah, so I mean, with a bit of, let's say, tools from operator theory, functional analysis, I mean, you can make a huge difference. And so now what we use is this convolutional operator. Okay, so then, I mean, the question is, I mean, what does it mean modeling the same phenomena? And modeling the same phenomena, we define the following way, that graphs represent the same phenomena are discretizations of the same metric space. Yeah? And so there's this correspondence between graphs and metric spaces. Again, you have points, here you have distances, and here you have weights. And if the distance between 2 points goes up, I mean, the h weight will go down. Okay, so let me now, I mean, show you the essence of the proof that indeed you get stability that way, and also how you get an error bound. So here we have two graphs which we now put through our neural network. So when we want to compare the repercussion on both graphs. Okay, so we have this nice metric space which overlays everything, and which we can use for transferring from one graph to the other. So now on the graph, on the continuous space, we put a function, a signal. Then we bring the signal down to both graphs, we sample, and now we use this filter, this convolution, which we defined. Yeah, remember the convolution was the function g, which we applied to the graph Laplacian, and by doing that, it immediately adapts to the structure of both graphs. Yeah. And now we bring it up again to our nice continuum space, and then we can compare it. Yeah, and so this is basically the essence of, I mean, everything. And now, I mean, the details are certainly much more complicated than I said here. Our analog domain will be borrowed space with a Laplacian. Our digital domain will be graphs with graph Laplacian. Then we will use Parley-Wiener spaces in that sense, which are defined on this continuum overlaying space. We have sampling operators and interpolation operators to bring everything back up. So let me just show you what we aim to obtain. So first, what you aim to obtain is, I mean, to compare if we just stay on the continuous space versus if you go down to the graph, and then we need to compare two different graphs. So this is half of the game, basically, to estimate this error. You see, we have here the signal on the continuous space. We bring it down. We apply our convolution operator. We bring it back up, and we compare it to if we stay on the continuous space. And we will show that this has this can be estimated by these two components. This is the error just of the Laplacian. So f is the identity here. And this is the consistency error, how dense the sampling is. And so this, I mean, since this looks extremely complicated, it's basically what I said on the previous slide. You see here, this is the transferability error, and you have these different components. This is the transferability error of the Laplacian, and this is the consistency error with certain components in front. Okay, and then, I mean, you can do that on both sides. So you have the continuous space on top, and you have now these two different graphs which you push through the neural network, and the ultimate result you see here. So you have these two graphs that you push through the neural network with the graph Laplacian. You have your graph convolutional neural network. You have the different graphs at each layer. And so the nice thing now is that this error, so it compares the error between the repercussion on both graphs. You have a very precise error bound now, which depends on the number of layers, on this Lipschitz constant. These are estimates from each of the layers, and here you have the dimension of Pauli-Wiener spaces. So you have a beautiful error bound, but not only that, you also have that these graph neural networks, so the function calculus graph convolutional neural networks behave often better than the spatial one. So here, as an example, you have images of different resolutions, and certainly all of those are discretizations of the same continuous image, so they are all in the same class. So they fit to our framework, and here you see the accuracy, and the blue line here is this functional calculus graph neural network, and this is the spatial one. So here it even behaves better. So with a bit of, let's say, functional analysis, operator theory, you can make a huge difference in this area. Okay, so let me now also talk just a little bit about explainability. I mean, this is, I think, an extremely important area, but it deserves a bit more mathematics. But it's highly interdisciplinary because, so if I ask you what is an explanation, I mean, everybody of you will give me a different answer. So, what is explainability? Explainability aims to understand how decisions are reached. In the easiest case, and it looks very simplistic, but this is to a certain extent where many areas of this area are, but I think from an operator theoretic viewpoint, maybe one can make, much more in that direction. So here, for instance, you have a 3 as an input. The neural network says correctly, this is a 3, and then you want to understand how the decision was reached. And what is then put on top is like a relevance map where each pixel indicates how strong or let's say how important that was for the decision. So here the neural network looked a lot at these red dots, but that makes sense because these openings distinguish a 3 from an 8. And so, but these blue parts played against the decision. So here the neural network did something reasonable. But from a mathematical viewpoint, these color images are nice to look at, but that's not satisfactory, isn't it? Because you would like to really know what is relevance, what about optimality, and also these pixel-based explanations. If you look at images, not every pixel will be important. It will be maybe structures of the image which are important. The ultimate vision of this whole area is to be able to discuss with a neural network how it reached a decision like you would discuss with a human. With ChatGPT, we are a bit further in that direction, but still we are very far. And from my viewpoint, which I think is also often neglected, maybe also because there are not enough mathematicians in this area, is the explainability approach has to be reliable itself. If we use it for ensuring reliability, then the approach itself has to be reliable, so it has to come with a mathematical foundation. Otherwise, it looks nice, but as we know, it will not be sufficient. Okay, so let me show you one approach which we developed, which is based on information theory, just in a nutshell. So that you get the flair of it. So information theory is an exciting area. I don't know who knows about it. I mean, in a nutshell, it does the following. Someone has a message, and she transmits it at a certain rate to another person who is always called Bob for some reason, and then he decodes it. Yeah, so how much she sends certainly depends on the error of how it is decoded. So if she sends not only few parts of this message, then the error will be large. So what she sends is the rate, and the error of decoding is the distortion. So there's this rate distortion trade-off. Now, we frame this explainability approach in this framework. Okay, so this person has a neural network, and he also has the same neural network. Alice has this image, that's the message. She transmits parts of the message to Bob, hopefully the relevant part. Then Bob obfuscates it, maybe by random pixels to not distort the meaning too much, and puts it through his neural network, and he will also get a decision, and this will make an error, and the error will be the smaller, the more important these pixels were. And that's what we want. So this is the error of distortion. So the difference between those. And what we aim for is we want to have very few pixels, but keep the distortion under control, to have a concise explanation. As this is a rate distortion function, you want to minimize the number of pixels which are sent while keeping the distortion under control. And if you work in optimization, I don't know if there's anyone in this area, you will know that you cannot compute that because that's NP hard. It's actually NPPP complete, so you need to relax that, like you would also do in inverse problems, for instance, or compress sensing. Compress sensing relaxed also from L0 to L1 norm. Instead of solving this, you solve this minimization problem. So you have here, again, the distortion. You have here the L1 norm, which also promotes sparsity. So you put, for every pixel, you have a relevance score, and you have this lambda as a parameter balancing between both. Okay, let me show you some examples. So if the neural network says this is a dog, then these are explanations where the network looked at. See here, I mean, the shape of the dog, which the head of the dog, which makes a lot of sense. So you see ours is tuned towards sparsity, very few pixels, explaining where the decision came from and how the decision was reached, and you can also compare that. For instance, compare different approaches. If you have here the rate of important pixels versus the error, you see that ours is tuned towards, with few pixels, getting also a small error. Now, where does applied harmonic analysis come in? I promised you there is some harmonic analysis in the game. So there are two problems. First of all, I mean, this looks very strange if you just obfuscate with random pixels. And secondly, why using pixels at all? And so, for the first, let me just believe me, I mean, there are neural networks which are able to in-paint that in a more natural way. But maybe more importantly, what one can do, certainly, I mean, using applied harmonic analysis, is to use a decomposition of the image, for instance, by wavelets, by shearlets, by systems which you know, and then put the relevance score on the coefficients of that. So that gives a much more natural decomposition, and it gives also very interesting results. But that's also very, very comparable to image compression. So if you work in this area of harmonic analysis, applied harmonic analysis, you might know how image compression works. You have here an input image, you compute your wavelet decomposition, you select the largest entries, you replace the others with 0, then you reconstruct, and then you hopefully get an image which is almost indistinguishable to the original image. And so this gives you here the high compression rates. Now, what we do here with this algorithm, where we use now wavelet decomposition, which we call cartoon X, because it's based on, let's say, cartoon-like ideas. You have here the input image, you compute your wavelet decomposition, you select the largest entries, which are hopefully the relevant ones. You replace now the others with random noise. And then the reconstruction looks certainly never like the original image, but through the lens of the neural network, it looks similar. And that's what you need. So this is in the spirit. Okay, so let me show you two fun examples in this direction. Just to give you a glimpse of what you can do with that. So this is an example from telecommunication. You have here a city map, let's say Canterbury, for instance, and you have here these red dots, let's say members of this conference, where everybody has a cell phone, and you know the cell phone reception, and then you have here the cell tower. And then the neural network computes this black and white background, which shows you the strength of the signal at each point. So here you have a really bad reception, because you have a lot of buildings obstructing your view to the cell tower. But then you see this very strange area here, which is an area of bad reception, although people who stand there stand in front of the cell tower. Yeah, so you can wonder whether the neural network did something wrong. And you can ask this explainability approach, and the explainability approach will tell you, well, the network based its decision on these buildings and these cell phone users. And in fact, they have bad reception. And so the network did something reasonable, and what turned later on out was there was a building missing in the city map. So the network did something correct, but the data was faulty. So this you can find out by explainability approaches. You can also find out why the neural network did something wrong. So here is a funny example. Here the network said this is a diaper. I mean, obviously not true. And this is a screw. And now, I mean, you can overlay the explanation, and you can see what the network has seen to reach that wrong conclusion. And so here, if you overlay it, it looks a bit like a baby, and then it can be mistaken for, well, I mean, relating to diaper, and this looks a bit like a screw. And then you can counteract to that. And so we also did that with shear alerts, and you can actually, the nice thing here is, because you have this approach based on information theory and applied harmonic analysis, you also can do rigid mathematics. You can show that these approaches don't introduce artificial errors, edges, and so on. Yeah, so you can really prove results in that direction. Okay, so let me just, in the very few last minutes, talk also a little bit about limitations, because that's very dear to my heart right now. And I think it's very important. And also, as said, I mean, if any one of you works in numerical mathematics, it's maybe something you might also consider what I will tell you about. And so deep neural networks are not a Swiss Army knife, they have limitations. And what I would like to look at is what happens, or what does the hardware we train our neural network on has as an impact. Because we have typically continuous problems, yeah, so imaging and so on, but then we break everything down to zeros and ones. And so it should have an impact, and since we also have a Turing college here, I thought that would be nice. I mean, here this deals with Turing machines. So there's this theory of computability. It's closely related to mathematical logic. So a computable problem is one for which the input-output relation can be computed on a digital machine, which is always a Turing machine, for any given accuracy. Okay, so now, I mean, inverse problems are a major area where we apply neural networks, and so this is a very classical problem. You have here your operator, or here in a discrete sense, your matrix. You have x, which you want to compute, and you have your measurements y. So you have the problem ax is equal to y, and you want to compute, you know a, you know y, you want to compute x. Solving undetermined linear system of equations. And so this is a typical approach to solve this. So you have here, you want to solve it as accurately as possible, and this is your regularization term, the L1 norm of your x. And so these are all solutions. And what you can show is that, unfortunately, this problem, so this function, is not computable on a Turing machine. Yeah, so that means you cannot compute it in a general form. I mean, you cannot design a general algorithm which computes this always for any given accuracy. So this seems a serious problem. Let me also say there's related work, I mean, also here from Cambridge, University of Cambridge, Anders Hansen, who actually use an Oracle Turing machine, which is a little bit weaker. Yeah, so that means, I mean, as said, there is no algorithm on digital hardware, so on a Turing machine, which computes this for any given accuracy. So this is a limitation not of the inverse problem, but of the hardware which we use, and it could point towards. Yeah, so I mean, if you see self-driving cars, we are not at that level which we anticipated at this point. But This could be the underlying problem why we are not as far as we want. But even worse, I mean, what we can show is could even be a systematic error of 1/4. Now, for every given accuracy, you will say, rightfully, there's a machine precision that will not work anyhow, but one can even show there's not a computable function, so this Banach-Mazur computability is even weaker, so that I might always have a systematic error. Yeah, so this is really bad. But here, I mean, let's say mathematics could show that there is a problem in the game, but we can also solve it. And what one can show is that, in fact, I mean, if we go to other types of computational approaches, like so-called Bloom-Schupf-Smale, yeah, so I think Smale might be known to everyone, machines which are analog computing systems, then things become computable. Yeah, and so this points now to a very exciting direction, because there is a lot of new hardware being developed, like neuromorphic computing, biocomputing, quantum computing, all in the direction of analog computing. Yeah, so what one can show mathematically, that there is a limitation and there could be a way out. You can also see right now that there are interesting developments in industry in that direction. And in fact, I mean, not overdoing my time, I mean, there are many directions where you can show these computability issues with classification problems. The pseudo-inverse is not computable. If you go to the area of PDEs and you have solutions of Laplace diffusion equations, there's complexity blow up, so that, I mean, the complexity you have for your input data, I mean, blows up exponentially during the computation, and also optimization problems. So the vision, my vision, and I think of many for the future, is to really get, I mean, truly reliable AI by mathematics, and in particular also going to analog computing. And let me also say something, because when the Vice Chancellor stood here, he said, I mean, University of Kent is very interesting in sustainability. This is very closely related to that, because, so this is a graph from the decadal plan of the Semiconductor Research Corporation in the US. What you see here is the world energy production. And here you see the energy we just need for communication, just for communication. And so see here, it will make a difference if you use CPUs, GPUs, maybe new platforms will make a difference, but if you don't do anything and use hardware and continue to use the classical hardware, we will reach the world energy production easily at some point within the next 10, 15 years. And so if you see the news, Microsoft builds a new GPU center in the US, and it builds the nuclear power plant right next to it. And so the hope is that with this analog computing, you can also get energy efficient AI in that direction. We also lately started a company, Ecologic Computing, in that direction. Let me just say in the last few minutes, since I said right in the beginning that this model for the human brain is very crude, there are more sophisticated mathematical models. So for instance, spiking neural networks, which are more continuous based. So where for a neuron, I mean, you have different, let's say, potentials which arrive at different times. So you have also the information is encoded in the timing. And so this is, I think, a very interesting direction for the future. So you can show results like that the complexity there for these neural networks is less than for the others. Okay, so I think my time is up. Some final thoughts from my viewpoint. I mean, we live in, concerning AI, in really exciting times. I mean, it shows impressive performance, but we still have this major reliability issue. And I think only mathematics can help here and can ensure that we get true reliability, but, I mean, a mathematical foundation is largely missing. And there are certain directions which are important for that, ensuring that expressivity, learning, generalization, explainability. I hope you also saw that basically many areas can make an edge. Here we looked a bit more at, let's say, applied harmonic analysis, operator theory, but basically, I mean, mathematics in its full breadth is needed there. We also talked a little bit about computability on digital hardware, but I think in general there are very exciting future perspectives from mathematics, and it's also really essential because AI is such a transformative technology. Since I talk now about reliability a lot, let me also mention just at the very last point that we just started a school, Konrad Zuse School of Excellence in Reliable AI in Munich. It's a structured master plus PhD program between both universities there, the TUM and the LMU where I'm at, and you see mathematical foundations here also plays a major role and is the basis for all of these applications. And with this I'd like to conclude, and thanks a lot for your attention. Oh, sorry.
Thank you very much, Gitta, for this very nice talk, and this very nice also introduction at the very beginning. Are there any questions? There's one question.
Hello, can you hear me?
Yes.
If we go back to the slides where you had the G delta and the C, the decomposition.
Oh, I know, you mean...
I think it was before, yes. Somewhere, yes, yes. So isn't it somewhat limiting to just look at those operators that are of the form G delta?
Is it limited to?
Like some kind of limitation of studying just such operators, such C, decomposition of such...
Yeah, thanks. So can you hear me if I speak to this? Okay, wow, okay, that's amazing. Yeah, thanks a lot for the question. I mean, I think that's a very, very good question. I agree with you that it's a bit limiting. I mean, one can do certainly better than that, but I mean, also from a computational viewpoint, I mean, this is doable and feasible. If one does more from an operator theoretic viewpoint, it might be that then one runs into computational problems. But I mean, it's worth exploring. So I mean, for our purposes, getting these error bounds, that was for now sufficient. But I mean, this is certainly not the end of the game.
Okay, thank you.
Thank you for the question. Any other questions? Yes.
Hello, Professor. I have a question. If I have model and use neural network method to learn a sample set, we can ensure that the model can be guaranteed to converge in the sample set. And I want to know how can we determine whether this local optimal solution is also globally optimal?
If I understood you correctly, you are asking about the training process? So you're asking about the training process. If you train the neural network, you end up in a local minimum, and if this is a global minimum of sorts, or is this what you're asking?
Yes. Yes, I want to ask that the local optimal. How to guarantee?
Yeah, I mean, I think it's also a very good question. Thank you for that. So it's, I mean, sometimes it's even that the local minima are better than a presumable global minima for certain reason. I mean, so you always need to choose. Yeah, so what you want is that you end up in a minimum which has good generalization properties. So where, I mean, then also, let's say, that the out of sample error is better. So this might not be, let's say, the best local minimum from a minimal viewpoint. And also there might not be, I mean, let's say an optimal global viewpoint. Yeah, so it's a highly non-convex problem. So in that sense, I mean, there's basically, I mean, I don't know of any approach where you can check whether you have the best in the end. So that's a delicate question.
Thank you.
Any more questions? Well, if not, then I think we thank Gitta again. Thank you very much.